change and ocean acidification as well. And I think that you will talk about marine ecosystems and climate change and modeling. So, if you're ready, Laurent, the floor is yours.
I'm ready. Good morning, everybody. Oh, yes, thanks, Renaud. No more echo. That's great. So, good morning, everybody. So, basically, what I intend to do is to build on what Olivier presented, the way we develop and we use biogeochemical model. But for myself, I will put those models into climate projections to look at potential impacts of climate change on key characteristics of marine biogeochemistry. So let me share my screen, if that works. Yes. So Renaud, do you see the full screen?
Yes, it's okay. Thanks.
Perfect. So as Renaud mentioned, I will talk about the impact of climate change on marine ecosystems, but I will also mention acidification and deoxygenation. So other key characteristics of the chemical environment of the ocean that may change or that are changing under anthropogenic pressure. So maybe as Renaud mentioned, I work at the global scale with climate models, so it will be a global perspective. So it won't be very detailed for regional scale interests, but many of the studies that deal with the regional scale are somehow built on what we do at the global scale. So they are coupled to what we do at the global scale. So there are still some interests on first understanding potential projections at the global scale and then translating that to the regional scale. So let me start with some very general considerations on the impact of climate change on marine ecosystems. This is a figure from the last report of the IPCC, the last special report of the IPCC on the ocean and the cryosphere, with this famous amber diagram that basically shows the risk of severe impacts on biodiversity, on the functions of the ocean and coastal ecosystems that are projected to be higher and higher for elevated temperature. And you see here a list of key ocean ecosystems, from coastal ones, warm water corals, kelp forests, seagrass meadows, but also epipelagic and open ocean ones. And you see that basically using models, using projections, we are able to qualitatively estimate the potential risks that these ecosystems may face under elevated global warming. So this is true in a very synthetic way in this diagram here, but we have ways to be much more specific. And I give you another example from, again, the last IPCC reports, here looking at the potential impacts of climate change on fisheries, and especially on fisheries catch potential. And you have here two maps showing the potential impacts of climate change on fisheries yield or fisheries catch potential for two different scenarios. And you see that under high or elevated global warming on the right, you have potential large decreases in fisheries catch potential in the tropics, especially that may range or may decrease up to minus 40 or 50% in some regions of the global ocean. And these declines in tropical fisheries or mid-latitude fisheries may be contrasted with increase in fisheries in some other regions of the ocean. And to do that, to do those projections, we need climate models, of course, but we also need biogeochemical models that are a key tools to translate the climate information into marine ecosystem projections. So that's what I want to describe in the coming slides. Again, describing very quickly the type of models we use in climate projections. So to do climate projections, you need basically two elements. You need a climate model, of course, which is what you have on the upper right. So within a climate model, you would have a representation of the atmosphere and of the ocean and the land surface. But in addition to the climate model, you need scenarios. And here you have examples of CO2 emissions scenarios for the next decades, from high emission scenario in brown here to high mitigation scenarios in which the CO2 emissions decrease sharply in the next decades. And when you combine those climate models that are forced with those emission scenarios, you can derive what we call climate projections And here you have basically a simple animation of changes in temperature anomalies in the coming years based on those climate models. So the way the scientific community has been organized in the past decades to do these climate projections, it's within this big project, which is called the SEMI project or Couple Model Intercomparison project that I guess many of you have heard about. And so within this project, we all perform the same simulations using the same scenarios. And so you have approximately about something like 40 different climate modeling centers that develop climate models and that run climate projections using the same scenarios. And then we intercompare those climate projections to get an idea of the uncertainties in terms of climate projections. And I'll come back on these uncertainties and how we try to explain or to reduce the uncertainties. So we have these big international projects that gather all the modeling centers around the world that develop climate models and perform climate projections. And a big change over the past years and past decade is that the climate models that started to be developed in the 60s and 70s, since the end of the 90s, start of the 2000s, they now include marine biogeochemical components. And the first reason for that was to be able to represent the carbon cycle and the ocean carbon sink and how the ocean carbon sink responds to future conditions. But the fact that climate models do include marine biogeochemical components basically opened the door for analyzing how climate change may impact marine ecosystems, marine phytoplankton productivity, to look at acidification, at the loss of oxygen in the ocean. I have here a few slides that probably Olivier already showed or discussed, which basically describe the evolution of the marine biogeochemical components that were used in climate models. So at the start, end of the 90s or start of the 2000s, the models that were used in climate models were very, very simple biogeochemical model. We could call them just geochemical model. Basically, all the biology was included in only one equation, only representing the exports of carbon across the base of the mixed layer, which is probably the most important characteristic that matters for the carbon cycle, that impacts the ocean carbon sink. And so some climate models still use this very simple biogeochemical scheme, only one equation, one nutrient, carbon, alkalinity, oxygen, and then transport of all these properties, as Olivier explained. But in the subsequent generation of climate models, those biogeochemical tools, they have evolved. Some models do include simple NPZD models. So one phytoplankton, one zooplankton, maybe one nutrient, nitrate or phosphate, plus particles and disturbed organic matter. And what we have now in some of the climate models are more complex biogeochemical scheme, still very simple, with several phytoplankton groups, several zooplankton groups, and several nutrients to be able to represent co-limitation by several nutrients. So the models we use in the climate, the marine biogeochemical components we use in the climate models are very similar to the ones that Olivier described in the previous lecture. So I will show you examples with the PISCES model that you've learned to use and that Olivier described in details. So now I've set the scene. We have climate models that do include ocean biogeochemical components, as this one, several nutrients, phytoplankton, zooplankton groups. And so this enables to project ocean acidification, to project deoxygenation, to project phytoplankton productivity in addition to ocean warming. And so this is what I will focus on in the next slides. So let me start by a few very simple projections here using not the latest generation, but the one before, CEMIP 5, which was used in the 5th assessment report of the IPCC published in 2013. And then I will show you the latest state of the art, how these projections have been updated with the most recent generation of climate models. So what you see here are typical representations of projections for sea surface temperature on the left and for sea surface pH on the right, you have different colors for different scenarios, from a high mitigation scenario in red to a low, from a high emission scenario in red to a high mitigation scenario in blue. And we always represent those projections the same way. The line is the average of all the models that did perform the projection, and the envelope around the line is an estimate of the uncertainty that is based on differences between the models. So it's typically plus minus one intermodal standard deviation. And so what you see here is that, of course, the projections of sea surface temperature at the global scale largely depends on the scenario, with more warming for the high emission scenario, much less warming for the high mitigation scenario, but still with large uncertainties for the same CO2 concentration pathways, the same other greenhouse concentration pathways. You see that for the projections of pH, we have also much more acidification in the high emission scenario than in the high mitigation scenario, but with much less uncertainty than for sea surface temperature. In fact, when you force these models with the same atmospheric CO2, they do project very similar acidification, at least for the ocean surface. So what you see here is warming and acidification with much less uncertainty on surface acidification than what we have on the warming side. If I now look at two other important properties of the ocean, deoxygenation on the left and changes in net primary production on the right, you also see that the models do agree on the sign of the change in oxygen in the ocean for the subsurface, with a decline of oxygen concentrations between 100 and 600 meters. That's what we call ocean deoxygenation. You also see that this decline depends on the scenario, with up to -3–4% of oceanic subsurface concentrations. What you may know also is that we can link this decline in oxygen to the change in the physics of the ocean, with less ventilation, a more stratified ocean, a warmer ocean, and this will decline the amount of oxygen that is transported in the interior. And on the right, you see that the models, they do project a decline in global NPP by up to -16–20% for some models, but with lots of uncertainties. The NPP projections here for the high emission scenario in red give you something between almost no change to -16 to -20%. So productivity will very likely decline. That's one of the conclusions of the special report on the ocean 2019, but with lots of uncertainties on the quantitative estimates of this decline of NPP. And just a few words again on the NPP decline that is projected by these models. Again, very similar to oxygen, this is linked to the increased stratification of the ocean, that would deliver less nutrients to the surface, that would increase nutrient limitation, and hence would lead to a subsequent decrease in NPP. Of course, these are global values for warming, for acidification, for oxygen, and for NPP, but these projections, they do vary a lot at the regional scale. And this is what you have on that map. So that's a composite map where you see the projections of all these properties, but you see in colors the regions that are the most affected by those modifications. So in red, the regions that would, under high emission scenarios, be affected by the most warming. That's the North Pacific, or here in the Equatorial Pacific. You see in blue here, the regions that would be the mostly affected by the decline in NPP. That's the case in the tropical ocean, tropical Atlantic, tropical Indian, tropical Pacific, but also in the North Atlantic. And the decline that are the most affected by acidification here is the Arctic Ocean. So we have some knowledge for the global scale, still with uncertainties, but also some knowledge at the regional scale, again with uncertainties. So what I will do in the coming half an hour or 20 minutes, I will save time for questions, is to first give you an update on these projections using the latest Earth system models. So basically coming back on what we find in the latest IPCC reports. How did those projections of warming, acidification, deoxygenation, and decline of NPP have evolved in the latest generation of climate models? Then I will briefly discuss the uncertainties in those projections. How do we understand those uncertainties? And do we have means to reduce the uncertainties when they are large? And then I will, in the last part, basically expand the uncertainties and to show you that we still have lots of processes that are not represented in these models and that may increase the uncertainties if taken into account for these projections. Okay, so that's the three parts of my presentation. So let's start with a quick update on the latest results from climate projections. So I'm basically comparing the CMIP5 generation, which was the basis for my introduction, with the latest generation, which is the CMIP6 generation of climate models. And maybe let me skip this. So the first point I'd like to make is in terms of evaluation of these models. So again, this is a very synthetic graph showing how the models perform as compared to observations, comparing the latest generation, CMIP6, to the newest generation, to the previous generation, CMIP5. So this comes from a paper by our colleague Roland Seferian, in which he compared those different models, and you see them here. IPSL is here using PSCES, but you see some of the other international models, one model from the UK ESM, from the Max Planck in Germany, CNRM, the other French model also using PSCES. And here, basically, we compare for different fields, mixed layer depths, but ocean carbon fluxes, surface chlorophyll, oxygen, nitrate, silicate. We compare scores in terms of evaluation between the CMIP6 version versus the CMIP5 version. So when it's in green, it means that the model has improved. Maybe because the physics is better, maybe because the biogeochemistry is better, maybe because the tuning has been performed better. But one of the conclusions of Roland Seferian here is that generally the models, they do perform better in CMIP6 than in CMIP5. It's not always true. You see some red boxes here, but generally the models do perform better. So there are lots of details that we could look at the regional scale and for the different models, but that would take ages, as you may imagine. So let me go now to the projections. So very similar plots than the ones I showed for CMIP5. What you have on the top left are warming projections, so sea surface temperature, surface pH, subsurface oxygen, and NPP. And what you see, of course, is that the models, the new generation of models, they still project warming, which are different for the different scenarios, ocean acidification, deoxygenation, and a decline in NPP. Again, the main processes that were responsible for these projections in the previous generation are the same that we identify now. So the warming is linked to heat penetration in the ocean, surface pH or surface acidification is linked to the ocean carbon sink. Ocean deoxygenation is, of course, linked to warming and to reduced ventilation, increased stratification, and the decline in NPP, mostly to the decline in nutrient supply linked to ocean stratification. When you look at the regional scale, again, the patterns are very similar to the ones we projected in the previous generation. So the regional patterns are consistent with previous studies. That's a figure from Lester Kwiatkowski paper in 2020, and you would find similar figures in the latest IPCC reports, again, using several models. You have projections of sea surface temperature, surface pH, subsurface oxygen, and phytoplankton primary productivity. And this is for the high emission scenario, the SSP 585, at the end of the 21st century. And you have an additional interesting feature on these plots. It's those stippling pattern, the dots that you have here. And the convention we use on that plot is that when you have this steepling pattern, it means that all models agree. They agree on the sign of change, and they agree somehow on the fact that the change would be higher than the natural variability. And what you see here is something very clear for warming and surface pH. The models do agree. It's kind of easy, of course. It's warming almost everywhere. It acidifies everywhere, and the models do agree both on the magnitude and on the sign of change, of course. For oxygen and NPP, you see that it's much less robust, especially for oxygen in the tropical oceans. The models don't agree, no steepling. They don't agree even on the sign of change. So we have lots of uncertainties in the projections of oxygen concentrations in the subsurface tropical ocean. And for NPP, it's even worse. You have many regions in the world ocean where the models don't agree. They don't agree in the sign of change. That's true for the tropical Pacific, for the subtropical Atlantic Ocean, for most of the Indian Ocean. And you have only a few regions where the models do agree for the sign of change of NPP in the coming decades. They do agree in the North Atlantic. They all project a decrease of NPP, and they partly agree also in the Southern Ocean with an increase in NPP in that specific region. So you see that even with the latest generation of models, so the models are different, and the projections are also very different with lots of uncertainties. So let me summarize some of these differences in terms of projections for those main patterns and differences between CMIP 6 and CMIP 5, so the latest generation as compared to the previous ones. So the first point here that I'd like to make is that as compared to CMIP 5, under the same type of scenarios, under the same radiative forcing, in CMIP 6, so in the latest generation, we have greater ocean warming. And this is linked to the fact that many of the new models, they have higher climate sensitivity. So they do warm much for the same radiative forcing. We have also greater ocean acidification. That's what you have here. The colored dots are for CMIP 6, and the black symbols are for CMIP 5. You see that in CMIP 6, we have more acidification than for CMIP 5 for similar scenarios. You see also in CMIP 6 greater deoxygenation. Compare the red dot in the high emission scenario to the black dot in CMIP 5. So greater ocean deoxygenation. We have greater nitrate decline in the surface ocean. Again, compare the red and the black. But we have lesser NPP decline. Lesser NPP decline with more uncertainties. Compare the vertical bar here around the red dot to the vertical black bar around the black dot. So that's a quick summary on the latest generation. So greater warming, greater deoxygenation, greater acidification, greater nitrate decline, but less NPP decline, which is kind of surprising. Let me try to explain some of these differences in the projections. So as I said before, the greater ocean warming is linked to the increase in the climate sensitivity of many models. They are much more sensitive, and so they project more warming for the same scenarios. The fact that we have greater ocean acidification is linked to the fact that the scenarios, they've been built a bit differently between CMIP 6 and CMIP 5. So basically for CMIP 5, here, for the same radiative forcing, you have lower CO2 concentrations. And so when you compare different scenarios in CMIP 6 and CMIP 5, because you have higher CO2 concentrations in CMIP 6, for the same radiative forcing scenario, you have higher acidification. The greater deoxygenation is linked to the fact that with greater ocean warming, you have more or larger reduction in solubility, but also larger changes in what we call apparent oxygen utilization. The greater nitrate decline is linked to enhanced stratification in CMIP 6, and the increased uncertainty in NPP is kind of uncertain. It's linked to the fact that we have more diverse model responses. and I will come back on that, the fact that some models do include some new processes that are largely uncertain. So I'll come back on these uncertainties and NPP in the coming slides. So first conclusion here on the state of the art in terms of projections using biogeochemical components of climate models. You see that we project warming, acidification, deoxygenation, and NPP decline, which of course largely depends on the extent of future emissions. And this is consistent with previous studies. The regional patterns of warming, acidification, deoxygenation, and NPP changes, they are mostly consistent with previous studies. But there are some regional scale differences when compared to the previous generations. And this is due to changes in the scenarios. It's due to higher climate sensitivity in the new models. And it's also due to changes in the biochemical model complexity. And I will illustrate that in a second. And the most importantly, perhaps, is the fact that we are not reducing projection uncertainties. And in some cases, these uncertainties are even increasing. And that's the case for NPP. So this is a concern because, as you may know, we use the NPP projections then to force ecosystem models and to project fisheries potential, for example, as I stated in my introduction. So I will give you maybe two examples now. The first one is basically trying to get some insights into why we have larger uncertainties in NPP projections. And then in my second example, I will focus on acidification. I will try to give you an example on how we can reduce uncertainties in those projections. And this is based on, this one has been published in 2022. So this is based on two recent papers. So my first example is about NPP projections. And I'm comparing here two versions of our climate model, the IPSL climate model, the one that did participate to CEMIP 5, which is IPSL CM5, and the one that did participate to CEMIP 6, which is IPSL CM6. In both cases, those two models did include PISCES as the biochemical component, but two different versions of PISCES. PISCES V1 in CEMIP 5 and PISCES V2 in CEMIP 6. You have here projections for the high emission scenario in terms of SST at the global scale and at the regional scale. What you see here is that despite the fact that we use different versions of the model and kind of different scenarios, we have a very consistent projections of SST, both at the global scale, kind of the similar warming, and at the regional scale, very similar patterns in terms of SST, projected SST. But for NPP, it's two different worlds. In the previous generation, CEMIP 5, the model was projected a decline in NPP. In the latest generation, we do simulate an increase of NPP. And when you look at the regional pattern, so this is CEMIP 5, mostly decreasing NPP in the tropics, and increasing NPP in the Southern Ocean, partly in the North Pacific and in the Arctic Ocean. Whereas in the latest generation, here for declining NPP, this is true for the equatorial regions, the North Atlantic, but you have many regions in the subtropics that do project increasing NPP. So the physics of the models is quite comparable, but the response of NPP is very divergent, very different. And we've been able to identify the response of a specific process, the response of N fixation. So this is again NPP. And so this is the response of N fixation that is parameterized a bit differently between the two models. And what you see here is that in the latest generation, in blue, global warming basically leads to a large increase of N fixation by disotrophs in the ocean that will fuel NPP in the subtropics. Hence, the increasing NPP that you see in the North Pacific, the South Pacific, subtropical Atlantic, and subtropical Indian. And you know, it's some subtle changes in the way we simulate N fixation, ratio between nitrate and phosphorus, between nitrogen and phosphorus in the subtropical gyres that drive the changes in NFix and the future low latitude NPP. So as Olivier explained, many of the processes that may be important are yet not in those models, and they may cause some large changes in the projections. So we need to continue updating the models and to explore those projections by looking at the potential effects of these processes. So, of course, this is not the end of the story. There are ways to reduce these uncertainties. I won't show you that for the NPP, but I will show you that with another example, okay? So we changed regions, we go to the Arctic Ocean, and we look at projections here for basically the anthropogenic carbon inventory in the coming decades in the Arctic Ocean. So this is done with the CMIP5 models. And so it's the amount of additional carbon that is stored in the Arctic Ocean for the next decades, all with the same scenario, but with different models. And you see that this is very different. Again, same atmospheric CO2, maybe same acidification at the surface, but when you go deeper in the water column, especially in the Arctic, you have large differences. So some models do store lots of additional carbon. That's the case of the green model here. And some other models, they do uptake and or store much less carbon in the Arctic Ocean. And this results into a huge uncertainty in the projections of deep acidification. And so here we are looking at aragonite undersaturation. So when the water starts to be undersaturated with respect to aragonite, with potential consequences on ecosystems, on especially calcifying organisms. And what you see here for the deep ocean is that depending on the amount of carbon the models store in the coming decades, the acidification thresholds would be reached much earlier in the coming century. So again, we are in a situation where the models do project acidification with very large uncertainties when you care about what happens in the deeper ocean, in the Arctic Ocean. And so what Jens Terrar did in this paper, 2020, is that he basically found the mechanisms, the reason why the models do differ in the coming decades in terms of anthropogenic carbon storage in the deep Arctic. And that's what you have here, contrasting two models. Maybe we look at the bottom panels first. That's the amount of anthropogenic carbon that is stored in the Arctic Ocean, integrated over the water column, comparing those two models, the IPSL1 and the Norwegian Earth System model on the right. And you see that they differ a lot. Almost no anthropogenic carbon stored in the IPSL model and much more in the Norwegian model. And Jens Terrar has been able to link these different behaviors to the fact that the models, they do ventilate the deep Arctic very differently. You have here at the surface very dense water in the Barents Sea that will basically feed or fuel the deep ocean in the coming decades with high or with carbon-rich waters, which is not the case in the IPSL model. The surface density is much lower, and so you have much less connection between the surface waters that are rich in anthropogenic carbon and the deeper waters. And so using this relationship between what we know about surface density of these waters today and what we project in terms of anthropogenic carbon in the coming decades, because we know and we observe the density anomalies in the surface ocean today, we can use this constraint to constrain the projections. And that's what Jens Terrar did in this paper. So basically you have here a relationship between the density anomalies at the surface in the Barents Sea in the different models. So each dot is one model, and the amount of anthropogenic carbon that is projected to be stored in the Arctic Ocean at the end of the 21st century, or the acidification threshold in the 21st century. And so the denser the waters, the sooner the acidification threshold is reached, and the less dense the water, the later this acidification threshold will be reached. And so if you use this intermodal relationship plus the constraints on the surface density that you have here from observations, you can reduce the projected acidification. And so in that paper, we showed that we're able, combining many models and some observations, to reduce the uncertainties by as much as 30% for carbon storage. And what we show here is by reducing these uncertainties, we project greater regional ocean acidification than previously projected. So I guess this is a lesson. We have different models that may project key components or key variables with large uncertainties. We have ways, we have techniques to reduce these uncertainties. And this is a good example. And this technique is what we call emergent constraint. Last part of my talk, maybe 5-10 more minutes, I will explore some other uncertainties that are not yet represented in models. And so we have to be open to some new discoveries. You know, maybe there is a new process that may be important, that is not yet in models, and that may have consequences for some of the projections I've showed before. So I will explore two of these uncertainties, one that is linked to physics, and specifically to the role of small-scale physics. And then I will briefly mention the role of variable stoichiometry. I don't know if Olivier discussed this variable stoichiometry, but we can come back on that. So the role of small-scale physics. So this is based on a recent paper by Damien Coepel, in which he explored the potential influence of flows that occur below the resolution of the Earth system model grid, specifically eddies and filaments. And these typical physical sub-mesoscale characteristics, they are not represented in models, in climate models, or with very simple parametrizations. Why? Because of computational constraints. You can't simulate the global ocean at 1/10 of a degree for decades, because that's just too heavy, too computationally expensive. And so what Damien Coepel did in this paper, with a model very similar to Pisces, it's a bit simpler to Pisces, is to explore the role of ocean horizontal resolution in projections using a very simple and idealized model configuration. So it's just a double gyre configuration. Basically, it's mimicking the North Atlantic with the subpolar gyre and the subtropical gyre. And because this is a reduced and idealized configuration, Damien was able to increase the resolution drastically from 1 degree on the top left here to almost 1/30th of a degree. And so at that resolution, 1/30th of a degree, you see emerging very fine scale structures like vortices, filaments, small eddies, etc., etc. And so he was able, with those 3 configurations, to perform very simple global warming projections, basically just increasing the temperature and seeing how the models and the biogeochemistry respond to these idealized global warming scenarios. And this is interesting because you can compare in the same framework different resolutions. You know, 1 degree, which is typical of the resolution we use in climate models, to 1/30th of a degree, which probably we won't reach before probably many, many years in climate models. And so what Damien Coepel showed in this paper is that basically by comparing those idealized simulations in this mid-latitude double gyre configuration, he showed that when you increase the resolution, you still have a decline of NPP in this region, but this decline is reduced. So you have much less decline when you have increased resolution than in the standard configuration at 1 degree resolution. So we still have the same process than the one that was identified in the global climate models. So with global warming, you have a more stratified ocean, less ventilation. And because of less ventilation and a more stratified ocean, you have less nutrient supply to the surface and reduced NPP. But what Damien shows is that when you have higher resolution, this reduced nutrient supply declines, and hence you have less of a decline of NPP by approximately 50%. And what Damien showed in that paper is that this sensitivity of the decline of NPP to the resolution basically stems from the high sensitivity of the nutrient transport to the model resolution. What are the processes that transport nutrient to the surface? And so these processes, they depend, of course, on the very small scale, but they also depend on how the small scale physics affects the general circulation in these models. And this seemed to be a very important process. So basically those results, they call for an improved representation of the role of eddies on nutrient transport to better constrain the future evolution of marine NPP. So there are lots of new processes to explore. The last one I'd like to mention is the role of variable stoichiometry. So maybe as Olivier explained, in many of these models, again, to save the costs of the computing, we have to make some very simple assumptions or simplistic assumptions. And one of the assumptions we make in PSCAS that we use for the projections that I showed before is the fact that the organic matter would keep the same stoichiometric ratio between carbon, nitrogen, and phosphorus, whatever the conditions. So the model is Redfieldian by nature, meaning that whatever the conditions, the ratio between nitrogen and carbon, phosphorus and carbon, would be the same in all the organic matter compartments of the model. And we know that it doesn't work like this in the real ocean. We know that in the subtropical gyres, the N2C or the P2C ratios are different than the ones we have in the subpolar gyres. And so thanks to Olivier Aumont, we have a new PSCAS version that we call the PSCAS quota version, in which there is an explicit representation of these variable stoichiometric ratios in the different organic matter pools. So in the nanophytoplankton, in diatoms, in picophytoplankton, you have now carbon, nitrogen, and phosphorus that are simulated independently. And this enables to explore the potential effects of variable stoichiometric ratios on the projections. So we did perform some additional simulations looking at projections with the PSCAS quota version. So if you take into account the possibility of these ratios to change in response to climate change, what's the potential effect on marine biogeochemistry? And what's been shown in Lester Kwiatkowski paper here is that at least at NPP, global NPP, this does not have a large effect on global NPP in carbon or nitrogen. But in fact, this has a large effect on what we call food quality, because the nitrogen to carbon or the phosphorus to carbon ratios, they decrease with climate change, and they decrease because the ocean is more N and P limited. And so this decreasing nutrient or food quality metrics, they may have some substantial effects on upper trophic levels and in the trophic amplification of biomass decline. So again, new processes that may have consequences for the projections of ecosystem biomasses, on fish biomass, and maybe on fisheries. Okay, maybe it's enough if we want to have some time for questions, but maybe my conclusion are that despite new and improved models, and it's been great to have biogeochemical components in climate models, because in addition to exploring the response of the ocean carbon sink to increasing CO2 and climate change, which was in fact the initial question. So in addition to exploring the carbon cycle, we've been able to explore the impacts of climate change on marine biogeochemistry, on phytoplankton productivity, and hence on the open ocean pelagic ecosystems. So despite all this and improved models, we still have very large uncertainties, in particularly on deep ocean acidification, on deoxygenation. I haven't talked a lot about that, and on NPP, especially at the regional scale. So when using those global models to force regional models with which you perform projections at the regional scale, be aware of the initial large uncertainties. That means that if you want to force a regional model, probably would be better to use different climate models as a way to, represent the uncertainties that stem from those climate model intercomparison projects. So I hope I convinced you that we have novel ways to both identify and reduce these projection uncertainties, using in particular these emergent constraint techniques, as I showed for the Arctic ocean acidification, there are still a myriad of new processes that need to be included and evaluated and constrained. As Olivier said, these models, they are not the reality, they are not the real world. And so there are, some way of representing what we believe is the real world, but with lots of uncertainties, because many of the processes are not well represented or are just absent for these models. So we still have lots of new processes to be included, to be evaluated, and to be constrained. I give you two examples with N fixation and small-scale physics. And we have new frontiers. The new frontiers, they are multifold. We need to work on shorter timescale. Everything that I showed you is basically end of the centuries or second part of the centuries, most of the time in high emission scenarios. But what's the situation for the next decade, the next 2 decades? So there are, a new domain, which is what we call decadal prediction, in which we try to use the same models, but to focus on the next decade, to see if there are ways to do predictions of the next years and decades. It's still what we call a gray zone. Then one of the new frontier is also to go from the global scale projections to regional and even coastal projections. And that's what you try to do with the CROCO model, for example. How can we perform or produce projections at the coastal scale, at the regional scale, that are meaningful? What are the boundary conditions that I use in addition to what's in my model? And again, using different models to explore the uncertainties seems absolutely key in that regard. And then the last bit, which I guess is also very important for projections at the regional scale, or especially in the coastal domain, is that in addition to the climate forcing, increasing greenhouse gases, maybe changes in aerosol emissions, you have other forcings that need to be taken into consideration. Maybe pollution, maybe change in habitats, maybe fisheries or other fisheries, etc., that may have impacts on what you model in your system. Okay, Renaud, Christian, that's all for me. And I hope, yes, we have some time for questions if you have some.
Yes, thank you very much, Laurent. Really nice talk. So, is there any question in the room or online? You can write it if you want in the chat, or you can raise your hand if you want. Yes, one question from Lionel.
I will put my
Okay. Just check.
Okay. Hi, Laurence. Thank you very much for your. Sorry, there is an echo.
Yeah, there's a small echo.
It's better now? No. And now?
Yes.
Okay, great. Yes, I have a question about the spatial resolution. So in the plot you showed, there is a 1 degree, 1/9 of a degree, and 1/27, if I remember correctly. And if I remember correctly again, there is not that much difference between the 1/9 of a degree and 1/27. So what does it mean? Does it mean that that we don't really care of semesoscale currents, or do we need to increase even more the spatial resolution?
Yes. I have an echo when I talk. Yeah, that's good now. Yes, so in this paper, effectively, there was a large difference between 1 degree and 1/9, and very little difference between 1/9 and 1/27. What I didn't say and what I should say is that the differences between 1 degree and then the higher resolution doesn't stem so much from the local scale processes, just the nutrient transport from the subsurface to the surface. Because you have, even if you don't have the very fine scale resolution, you have compensating mechanisms in the coarse resolution models just by vertical diffusion, but it stems from the impacts of the fine scale resolution on the large scale circulation. So the large scale circulation in the models, like the thermohaline circulation, and its change in response to global warming is different because of the resolution. So you start from different conditions, and you have a different effect of global warming in that configuration on the decline of this thermohaline circulation. So the ventilation declines less when you have higher resolution. And this effect seems to saturate. So there is a strong effect from 1 to 1/9 and much less when you go from 1.9 to 127. So my feeling is that it may be very specific to this region because it's linked to the global scale or to the large scale circulation and not to the very detailed small scale processes that transport nutrients from the subsurface.
So it's more an upscaling. Sorry. It's more an upscaling effect than a direct effect of fan scale features. Okay, great.
Absolutely.
Thank you.
So it means that we first have to basically to solve these upscaling issues. What's the impact of small scale physics on the large scale circulation and how the small scale physics would modify the way the large scale circulation responds to climate change. So if we have the good parameterizations, maybe we have some hope to be able to solve that without running the model at 1/30th of a degree.
Thank you.
So any other question in the room? Yes?
Also video.
Okay. My question's maybe less scientific, but more political. But is there a danger in increasing the complexity of the models and increasing then you have more uncertainty in your projections, and then if it's going to be used in these impact assessments, if you're producing these projections with a lot of uncertainty, can it maybe take away some of the power of these projections by increasing the complexity? Does that make sense?
Absolutely, it makes sense, and it's a question that we have to ask ourselves. But I guess we have to work at the same time on exploring potential uncertainties that are linked to processes that are not yet represented in models. And at the same time, we have to do as much as we can to reduce the uncertainties by using some of the techniques I mentioned, or by working more on some specific processes that seem to increase the uncertainty. Okay, so let me maybe give you a more clear example. We've been developing a lot those biogeochemical components, going from the very, very simple model that we have to the much more complex models that I showed in the end, with variable stoichiometry, lots of different phytoplankton types, etc. One good news, I would say, is that in terms of the potential feedback of climate change on the ocean carbon sink, okay, the response has not changed dramatically, and even the uncertainties has not changed dramatically from the early models. So somehow what we've been able to show is that even if we complexify the biological components, at least for the next decades, the potential impact on the ocean carbon sink doesn't seem to be first order. Okay, for the response of NPP, it's another story. And parameterizing N fixation in a bit different way gives changes completely the sign of the NPP projection. We need to be aware of that. So I think I would continue to argue that we need to do both, exploring new processes, potentially increasing the uncertainties, and at the same time, when we have uncertainty, work on the mechanisms that explain the uncertainty and trying to reduce the uncertainties. And there are ways to do that. And yes, we need to do that.
Thank you.
I have seen the question on the chat that I can respond to, Renaud, if that's okay.
Yes, okay.
Yes.
But I think you have already mentioned it, but you can come back on this.
I can come back on it very quickly.
Yeah.
Why is the uncertainty in pH, surface pH and SST very different? So the surface pH basically is very easy to model and have only one forcer, one driver, which is atmospheric CO2. Okay, so in the climate models, in those projections, it's the same atmospheric CO2 for all models. So it's the exact same forcing. Okay, and then we know very well the carbonate chemistry. So we know very well how the ocean chemistry responds to atmospheric CO2, and all the models, they do simulate this very similarly. So there is almost no uncertainty for surface pH. It's not true for deep pH, because then the way your model will ventilate differ quite a lot in the different models. For SST, even if you have the same CO2, the same methane concentrations, maybe the same aerosol emissions, going from the same greenhouse gas emissions to radiative forcing, already there you have differences between models. And then going from radiative forcing to warming, lots of differences between models because they don't have the same climate sensitivities. So by nature, the projections of SST in those scenarios is much more uncertain than the projections of pH. Yes.
Okay, thank you. Any other question? No? Okay, no more question online, I guess. Oh, see, yes, maybe one. Okay, okay, just to say thanks. Okay, okay. I think, thank you very much. So, Laurent?
Thanks to you.
Yes.
Have a good modeling practical. Is this what you do now?
Yes.
Excellent. Okay,
okay,
bye-bye.
Thanks for your inputs on the regional modeling.
Yes.
It was really nice. Okay, thank you. Bye-bye.
Bye.